In mathematics and computer algebra, factorization of polynomials. A polynomial factorization is the process of expressing a polynomial with coefficients in a given field or in the integers as the product of irreducible factors with coefficients in the same domain. Polynomial factorization is one of the fundamental tools of the computer algebra systems. The history of polynomial factorization starts with Hermann Schubert, who in 1793 described the first polynomial factorization algorithm, and Leopold Kronecker, who rediscovered Schubert's algorithm in 1882 and extended it to multivariate polynomials and coefficients in an algebraic extension. But most of the knowledge on this topic is not older than circa 1965 and the first computer algebra systems. In a survey of the subject, Erich Kaltofen wrote in 1982, see the bibliography below. When the long-known finite-step algorithms were first put on computers, they turned out to be highly inefficient. The fact that almost any linear multivariate polynomial of degree up to 100 and with coefficients of a moderate size, up to 100 bits, can be factored by modern algorithms in a few minutes of computer time indicates how successfully this problem has been attacked during the past 15 years. Nowadays, modern algorithms and computers can quickly factor univariate polynomials of degree more than 1000, having coefficients with thousands of digits. Formulation of the question. Polynomial rings over the integers or over a field are unique factorization domains. This means that every element of these rings is a product of a constant and a product of irreducible polynomials, those that are not the product of two non-constant polynomials. Moreover, this decomposition is unique up to multiplication of the factors by invertible constants. Factorization depends on the base field. For example, the fundamental theorem of algebra, which states that every polynomial with complex coefficients has complex roots, implies that a polynomial with integer coefficients can be factored with root-finding algorithms into linear factors over the complex field C. Similarly, over the field of reals, the irreducible factors have degree at most 2, while there are polynomials of any degree that are irreducible over the field of rationals Q. The question of polynomial factorization makes sense only for coefficients in a computable field, whose every element may be represented in a computer and for which there are algorithms for the arithmetic operations. Froelich and Shepperson have provided examples of such fields for which no factorization algorithm can exist. The fields of coefficients for which factorization algorithms are known include prime fields, i.e., the field of rationals and prime modular arithmetic, and their finitely generated field extensions. Integer coefficients are also tractable. Kronecker's classical method is interesting only from a historical point of view. Modern algorithms proceed by a succession of square-free factorization, factorization over finite fields, and reductions, from the multivariate case to the univariate case, from coefficients in a purely transcendental extension to the multivariate case over the ground field. See below. From coefficients in an algebraic extension to coefficients in the ground field. See below. From rational coefficients to integer coefficients. See below. From integer coefficients to coefficients in a prime field with p elements. For a well-chosen p. See below. Primitive part content factorization. In this section, we show that factoring over q, the rational numbers, and over z, the integers, is essentially the same problem. The content of a polynomial pz, x, denoted cont p, quote, is, up to its sign, the greatest common divisor of its coefficients. The primitive part of p is prim part p equals p cont p, which is a primitive polynomial with integer coefficients. This defines a factorization of p into the product of an integer and a primitive polynomial. This factorization is unique up to the sign of the content. It is a usual convention to choose the sign of the content such that the leading coefficient of the primitive part is positive. For example, minus 10x2 plus 5x plus 5 equals minus 2x2 minus x minus 1. Display style 10x2 plus 5x plus 5 equals minus 5. See dot 2x2 x1 backslash closing curly bracket is a factorization into content and primitive part. Every polynomial q with rational coefficients may be written q equals p c. Display style q equals frac p c closing curly bracket, where p z x and c z. It suffices to take for c a multiple of all denominators of the coefficients of q. For example, their product, and p equals cq. The content of q is defined as cont q equals cont p c. Display style text cont q equals frac text cont p c closing curly bracket, and the primitive part of q is that of p. As for the polynomials with integer coefficients, this defines a factorization into a rational number and a primitive polynomial with integer coefficients. This factorization is also unique up to the choice of a sign. For example, 1, 3, x 5 plus 7, 2, x 2 plus 2, x plus 1 equals 1, 6, 2, x 5 plus 21, x 2 plus 12, x plus 6. Display style frac 1 3 x caret 5 plus frac 7 2 x caret 2 plus 2x plus 1 equals frac 1 6 2x caret 5 plus 21x caret 2 plus 12x plus 6 closing curly bracket is a factorization into content and primitive part. Gauss proved that the product of two primitive polynomials is also primitive. Gauss's lemma. This implies that a primitive polynomial is irreducible over the rationals if and only if it is irreducible over the integers. This implies also that the factorization over the rationals of a polynomial with rational coefficients is the same as the factorization over the integers of its primitive part. On the other hand, the factorization over the integers of a polynomial with integer coefficients is the product of the factorization of its primitive part by the factorization of its content. In other words, integer GCD computation allows to reduce the factorization of a polynomial over the rationals to the factorization of a primitive polynomial with integer coefficients, and to reduce the factorization over the integers to the factorization of an integer and a primitive polynomial. Everything that precedes remains true if Z is replaced by a polynomial ring over a field F and Q is replaced by a field of rational functions over a F in the same variables, with the only difference that up to her sign must be replaced by up to the multiplication by an invertible constant in F. This allows to reduce the factorization over a purely transcendental field extension of F to the factorization of multivariate polynomials over F. Square-free factorization. If two or more factors of a polynomial are identical to each other, then the polynomial is a multiple of the square of this factor. In the case of univariate polynomials, this results in multiple roots. In this case, then the multiple factor is also a factor of the polynomial's derivative. with respect to any of the variables, if several. In the case of univariate polynomials over the rationals, or more generally over a field of characteristic 0, Un's algorithm exploits this to factorize efficiently the polynomial into factors that are not multiple of a square and are therefore called square-free. To factorize the initial polynomial, it suffices to factorize each square-free factor. Square-free factorization is therefore the first step in most polynomial factorization algorithms. Un's algorithm extends to the multivariate case by considering a multivariate polynomial as an univariate polynomial over a polynomial ring. In the case of a polynomial over a finite field, Un's algorithm applies only if the degree is smaller than the characteristic, because, otherwise, the derivative of a non-zero polynomial may be 0 over the field with p elements. The derivative of a polynomial in Xp is always 0. Nevertheless, a succession of GCD computations, starting from the polynomial and its derivative, allows one to compute the square-free decomposition. See polynomial factorization over finite fields #square-free factorization. Classical methods. This section describes textbook methods that can be convenient when computing by hand. These methods are not used for computer computations because they use integer factorization, which at the moment has a much higher complexity than polynomial factorization. Obtaining linear factors. All linear factors with rational coefficients can be found using the rational root test. If the polynomial to be factored is a n x n plus a n minus 1 x n minus 1 plus a 1 x plus a 0, display style a underscore n x caret n plus a underscore n 1 x caret n 1 plus c dots plus a underscore 1 x plus a underscore 0. Then all possible linear factors are of the form b 1 x minus b 0, display style b underscore 1 x b underscore 0, where b 1, display style b underscore 1, is an integer factor of a n, display style a underscore n, and b 0, display style b underscore 0, is an integer factor of a 0, display style a underscore 0. All possible combinations of integer factors can be tested for validity, and each valid one can be factored out using polynomial long division. If the original polynomial is the product of factors, at least two of which are of degree 2 or higher, this technique only provides a partial factorization. Otherwise the factorization is complete. In particular, if there is exactly one nonlinear factor, it will be the polynomial left after all linear factors have been factorized out. Note that in the case of a cubic polynomial, if the cubic is factorizable at all, the rational root test gives a complete factorization, either into a linear factor and an irreducible quadratic factor, or into three linear factors. Kronecker's method. Since integer polynomials must factor into integer polynomial factors, and evaluating integer polynomials at integer values must produce integers, the integer values of a polynomial can be factored in only a finite number of ways, and produce only a finite number of possible polynomial factors. For example, consider f x equals x 5 plus x 4 plus x 2 plus x plus 2. Display style f x equals x caret 5 plus x caret 4 plus x caret 2 plus x plus 2. If this polynomial factors over z, then at least one of its factors must be of degree 2 or less. We need 3 values to uniquely fit a second-degree polynomial. We'll use f0 equals 2, displaystyle f0 equals 2, f1 equals 6, displaystyle f1 equals 6, and f minus 1 equals 2, displaystyle f minus 1 equals 2. Note that if one of those values were 0, then you already found a root, and so a factor. If none are 0, then each one has a finite number of divisors. Now, 2 can only factor as 1 times 2, 2 times 1, minus 1, times minus 2, or minus 2 times minus 1. Therefore, if a second-degree integer polynomial factor exists, it must take one of the values 1, 2, minus 1, or minus 2, at x equals 0, displaystyle x equals 0, and likewise at x equals minus 1, displaystyle x equals minus 1. There are 8 different ways to factor 6. 1 for each divisor of 6. So there are 4 times 4 times 8 equals 128 possible combinations, of which half can be discarded as the negatives of the other half, corresponding to 64 possible second-degree integer polynomials that must be checked. These are the only possible integer polynomial factors of f x, displaystyle f x, closing curly bracket. Testing them exhaustively reveals that p x equals x2 plus x plus 1, displaystyle p x equals x caret 2 plus x plus 1, constructed from p0 equals 1, displaystyle p0 equals 1, p1 equals 3, displaystyle p1 equals 3, and p minus 1 equals 1, displaystyle p minus 1 equals 1. Factors f x, displaystyle f x, closing curly bracket, dividing f displaystyle f by p displaystyle p gives the other factor q x equals x3 minus x plus 2, displaystyle q x equals x caret 3 x plus 2, so that f equals pq, displaystyle f equals pq. Now one can test recursively to find factors of p displaystyle p and q displaystyle q. It turns out they both are irreducible over the integers, so that the irreducible factorization of f displaystyle f is f x equals p x q x equals x 2 plus x plus 1 x 3 minus x plus 2, displaystyle f x equals p x q x equals x caret 2 plus x plus 1 x caret 3 x plus 2, closing curly bracket. Then der Werden. Sections 5.4 and 5.6. Modern methods. Factoring over finite fields. Factoring univariate polynomials over the integers. If f x displaystyle f x closing curly bracket is a univariate polynomial over the integers, assumed to be content-free and square-free, one starts by computing a bound b displaystyle b such that any factor g x displaystyle g x closing curly bracket will have coefficients of absolute value bounded by b displaystyle b. This way, if m display style m is an integer larger than 2b display style 2b, and if g x display style g x closing curly bracket is known modulo m display style m, then g x display style g x closing curly bracket can be reconstructed from its image mod m display style m. The Zassenhaus algorithm proceeds as follows. First, choose a prime number p display style p such that the image of f x display style f x closing curly bracket mod p display style p remains square free and of the same degree as f x display style f x closing curly bracket. Then factor f x display style f x closing curly bracket mod p display style p. This produces integer polynomials f1 x f r x display style f underscore 1 x f underscore r x closing curly bracket, whose product matches f x display style f x closing curly bracket mod p display style p. Next, apply Hensel lifting. This updates the f I x display style f underscore I x closing curly bracket in such a way that now their product matches f x display style f x closing curly bracket mod p a display style p caret a, where a display style a is chosen in such a way that p a display style p caret a is larger than 2b display style 2b modulo p a display style p caret a. The polynomial f x display style f x closing curly bracket has up to units 2 r display style 2 caret r factors for each subset of f1 x f r x display style f underscore 1 x f underscore r x closing curly bracket. The product is a factor of f x display style f x closing curly bracket mod p a display style p caret a. However, a factor modulo p a display style p caret a need not correspond to a so-called true factor. A factor of f x display style f x closing curly bracket in z x display style z x closing curly bracket for each factor mod p a display style p caret a. We can test if it corresponds to a true factor, and if so, find that true factor, provided that p a display style p caret a exceeds 2b display style 2b. This way, all irreducible true factors can be found by checking at most 2 r display style 2 caret r cases. This is reduced to 2 r minus 1 display style 2 caret a1 cases by skipping complements. If f x display style f x closing curly bracket is reducible, the number of cases is reduced further by removing those f I x display style f underscore I x closing curly bracket that appear in an already found true factor. Zassenhaus algorithm processes each case, each subset, quickly. However, in the worst case, it considers an exponential number of cases. The first polynomial time algorithm for factoring rational polynomials has been discovered by Lenstra and Lovis and is an application of Lenstra-Lovis lattice basis reduction algorithm, usually called LLL algorithm. Lenstra and Lovis 1982. A simplified version of the Lll factorization algorithm is as follows. Calculate a complex, or p-adic, root alpha of the polynomial f x, displaystyle f x, closing curly bracket, to high precision. Then use the Lenstra-Lovis lattice basis reduction algorithm to find an approximate linear relation between 1, alpha, alpha 2, alpha 3, with integer coefficients, which might be an exact linear relation and a polynomial factor of f x, displaystyle f x, closing curly bracket. One can determine a bound for the precision that guarantees that this method produces either a factor or an irreducibility proof. Although this method is polynomial time, it was not used in practice because the lattice has high dimension and huge entries, which makes the computation slow. The exponential complexity in the algorithm of Zassenhaus comes from a combinatorial problem. How to select the right subsets of f1 x f r x displaystyle f underscore 1 x f underscore r x closing curly bracket. State-of-the-art factoring implementations work in a manner similar to Zassenhaus, except that the combinatorial problem is translated to a lattice problem that is then solved by LLL. In this approach, LLL is not used to compute coefficients of factors. Instead, it is used to compute vectors with r displaystyle r entries in R1 that encode the subsets of f1 x f r x displaystyle f underscore 1 x f underscore r x closing curly bracket that correspond to the irreducible true factors. Factoring over algebraic extensions. Trage's method. We can factor a polynomial p x k x displaystyle p x in k x closing curly bracket, where the field k displaystyle k is a finite extension of q displaystyle mathbar q. First, using square-free factorization, we may suppose that the polynomial is square-free. Next we write L equals k x slash p x displaystyle L equals k x p x closing curly bracket explicitly as an algebra over q displaystyle mathbar q. We next pick a random element alpha L displaystyle alpha in L by the primitive element theorem. Alpha displaystyle alpha generates L displaystyle L over q displaystyle mathbar q with high probability. If this is the case, we can compute the minimal polynomial q y displaystyle q y in mathbar q y closing curly bracket of alpha displaystyle alpha over q displaystyle mathbar q. Factoring q y equals I equals 1 n q I y displaystyle q y equals prod underscore I equals 1 caret n q underscore I y closing curly bracket over q y displaystyle mathbar q y closing curly bracket. We determine that L equals q alpha equals q y slash q y equals I equals 1 n q y slash q I y display style L equals mathbar Q alpha equals mathbar Q Y equals prod underscore I equals 1 caret N mathbar Q Y Q underscore I Y closing curly bracket. Notice that L display style L is a reduced ring since P X display style P X closing curly bracket is square free, where alpha display style alpha corresponds to the element y dot y display style y L dots y closing curly bracket. Note that this is the unique decomposition of L display style L as a product of fields. Hence this decomposition is the same as I equals 1 m k x slash p I x display style prod underscore I equals 1 caret m k x p underscore I x closing curly bracket, where p x equals I equals 1 m p I x display style p x equals prod underscore I equals 1 caret m p underscore I x closing curly bracket is the factorization of p x display style p x closing curly bracket over k x display style k x closing curly bracket by writing x L display style x in L and generators of k display style k as a polynomials in alpha display style alpha. We can determine the embeddings of x display style x and k display style k into the components q y slash q I y equals k x slash p I x display style mathbar q y q underscore I y equals k x p underscore I x closing curly bracket by finding the minimal polynomial of x display style x in this ring. We have computed p I x display style p underscore I x closing curly bracket and thus factored p x display style p x closing curly bracket over k display style k closing curly bracket. See also factorization section polynomials for elementary heuristic methods and explicit formulas. Bibliography Froelich, A. Shepperson, J. C. 1955. On the factorization of polynomials in a finite number of steps. Mathematische Zeitschrift. 62. 1. 331-334. DOI. 10.1007, BF01180640. ISSN 00255874. Traeger, B. M. Algebraic Factoring and Rational Function Integration. Proc. SMSAC 76. Bernard Bozemi. Per and Flo. Paul Wang. October 1994. Quantitative estimates for polynomials in one or several variables. From analysis and number theory to symbolic and massively parallel computation. Mathematics Magazine. 67. 4. 243-257. DOI. 10.2307 2,690,843. JSTOR 2,690,843. CS1 maint. Multiple names. Authors list. Link. Accessible to readers with undergraduate mathematics. Cohen, Henry. 1993. A Course in Computational Algebraic Number Theory. Graduate Texts in Mathematics. 138. Berlin, New York, Springer Verlag. ISBN 978-3-540-55640-4. Mr. 1228206. Kaltofen, Erich. 1982. Factorization of Polynomials. In B. Buchberger, R. Luz, G. Collins. Computer Algebra. Springer Verlag. CITES X 10.1.1.39.7916. Nuth, Donald E. 1997. 4.6.2 Factorization of Polynomials. Semi-numerical algorithms. The Art of Computer Programming. 2. 3rd ed. Reading, Massachusetts. Addison Wesley. pp. 439-461. 678-691. ISBN 0-201-89684-2. Lenstra, A. K. Lenstra, H. W. Lovis, Laszlo. 1982. Factoring Polynomials with Rational Coefficients. Mathematicianalin. 261. 4. 515-534. DOI. 10.1007, BF01457454. ISSN 00255831. Mr. 682664. Bin der Waarden. Algebra. 1970. Trans. Blum and Schulenberger. Frederick Ungar. Further reading. Kaltofen, Erich. 1990. Polynomial Factorization 1982-1986. In D. V. Chudnovsky. R. D. Jenks. Computers in Mathematics. Lecture Notes in Pure and Applied Mathematics. 125. Marcel Decker, Inc. CITES X 10.1.1.68.7461. Kaltofen, Erich. 1992. Polynomial Factorization 1987-1991. Proceedings of Latin, 92. PDF. Spring Elect. Notes Compute. Sci. 583. Springer. Retrieved October 14, 2012. Ivanyoz. Gabor. Marek. Karpinski. Saxena. Nitin. 2009. Schemes for Deterministic Polynomial Factoring. Proc. Isaac 2009. 191-198. DOI. 10.1145 1,576,700 seconds. 1,576,730.